I want to get into another perception topic called motion perception, and this is obviously very important for virtual reality. You can of course look at static panoramas in virtual reality, but our perception of motion is really fundamental to the kinds of things that we do all over the place in virtual reality. So that's the next big topic, motion perception. And remember, as I said last time, it's kind of a template. You know, there's X perception, where X may be all sorts of things, depth, scale, motion, color, on and on and on. So we may also apply the same concept to hearing or touch. So perception of different kinds of textures, for example. So this is again, as we go through these pathways from the sense organ all the way up to the higher parts of the brain, there's some hierarchical processing going on, and there's a perceptual process in there. And that's what we're trying to get an understanding of and trying to characterize. So what are the purposes for motion perception? Some of the main purposes. Well, one of them is segmentation or segregation. In other words, we might like to know, if we're looking at a scene in the jungle, let's say, we might like to know that there's an animal that's moving there, right? So the perception of that motion is very important, and you might imagine for evolutionary reasons it's very important, right, to know if there's something moving in the jungle, right, or in the forest that's about to, I don't know, potentially eat you, let's say, right? So it's very important to identify that. So perceiving that motion among a static background is very important, and you might notice that our eyes tend to fixate very quickly on something that's moving. In modern times, our ability to detect a moving car or cycle or some other vehicle that may be dangerous to us as we cross the road is also important, right? So it has a similar kind of purpose. So we're very good at extracting some object that's moving from a background that's stationary. Another purpose is to extract 3D structure. 3D structure of an object from the motion. So for example, you know, if I see this book moving around in some way, I get some idea about its structure. This book doesn't have a very complex structure, but take something, you know, much more complicated, like a chair with legs and such, move it around, and you get an idea of its structure just from the way it's moving around on your retina, right? There's some two-dimensional image that's changing on your retina, but you can infer three-dimensional structure. You can learn a lot about that. It's almost as good as if you walked up and started probing the object with your arms and use all of that information to try to build a 3D picture. So we're very good at building 3D pictures somehow in our minds of objects that we've not maybe ever seen exactly before, but we're using a lot of prior information, again, prior bias, and from the context we have a lot of information about how the light's falling on it in a certain setting that we're familiar with, and we make judgments about its three-dimensional shape. You can make illusions and fool the brain in some cases and get some false conclusions, but nevertheless we rely on this very carefully, very frequently in a large number of settings. And finally, another key purpose is visual guidance of action. And this is exactly part of where I wrote on scale perception here, one of the important aspects, reaching out and grabbing something. So if we want to reach out and grab something, then we are using motion, and we're using motion perception. We're perceiving the motion of our hand as we reach and grab something, and that visual feedback helps us to accomplish the task. So visual guidance of our actions. So that's useful for manipulation, like grab a cup. General hand-eye coordination, and may provide information about you know, other kinds of self-motion. Questions about that? I'm going to cover a couple more topics, and then I want to get to one of the main aspects of this perception of motion, which is going to be frames per second. I really would like to talk about that because that's obviously something that's on our brains a lot. We talk about this in connection to the lab, the virtual reality lab, and we'd like to know how many frames a second are enough, but I want to give a few more basic concepts first. So one thing that I find fascinating is if we look at the neural circuitry, Remember we talked about the visual pathways from photoreceptors all the way up to the visual cortex. So along that path, and actually very early in the path, we have the following kind of circuitry. So suppose there's an object that's going to go moving across the retina. There's some object. It goes moving across the retina. And imagine that there are neural detectors, let's say. So somewhere back here there's a detector A and a detector B. So imagine this neuron fires whenever the object moves across this location, and as the object moves across the location here, this one fires. So which one's going to fire first? Well, first A fires, then B fires. What's interesting is there's extra neural circuitry that looks like the following. It goes through here. There's a box that I'm going to describe in a minute, and then these feed together to some third neural structure called, let's say, C. And inside of this box is a delay, say some delta t, perhaps it's 50 milliseconds. So what happens here is this C fires if both A and B fire, but only if A fired a little bit ago. So A fires a little while ago and B is firing right now. The superposition of those in time, right, A a little while ago and then B right now, will fire C. So that's a very, very simple motion detector. So we have those all over the place for varying speeds and various distances, neighboring distances. And so one interesting outcome of that is that you're able to fool this sense by something called the wagon wheel effect. Which, if you've ever made some kind of pattern like the following, let's see, you put some stripes around the rim of a wheel and then you spin the wheel, it may start to look like it's rotating backwards even though it's going forward. So this is interfering with the basic operation of this neural circuitry. It's easy to fool it into thinking that it's going in the opposite direction because it's just based on very simple timings and the flashings of neighboring let's say the kind of, in some sense, the flashing or signal appearing in various spots along your retina and those photoreceptors responding. So, so you can very easily fool it into thinking reverse directions, unless there's a more coherent picture of moving from place to place to place to place along a very long sequence. So this is very interesting, I think. Also, one thing to think about is object motion versus observer motion. This is one of the key ingredients to avoiding simulator sickness if you're not careful. So if I just were to look at the images, if I could somehow make a recording of the images that hit your array of photoreceptors, right, and we imagine we're just going to play a video back now of what's hitting your photoreceptors, I might see some kind of motion occurring there, but how do I know if that motion is due to you moving or some object in the scene moving? Could be some combination of the two, but let's suppose it's one or the other. How would I distinguish between the two? If I were just watching the video, I don't think there's any way to fully distinguish that, right? Unless there's, well, okay, maybe you would start to guess from the context what's probably happening and use your powerful brains to make an inference. But if you just look at the raw data, there may not be enough there to really make the judgment. Let me give a simple example. Let's suppose we have an eye looking upward. All right, so draw the cornea sticking out here. And I have an object that moves from right to left. So it's moving along like this. So if I draw out the retina of the eye, I guess when the object's over here on the right, then there's an image of it over here on this part of the retina. And then when it moves across, it ends up over on this part of the retina. Not drawing too careful of a diagram here, but I think you'll understand the principle. Getting really curvy here. Yeah. So as the object moves from right to left, imagine the eye is held fixed and then the image goes from left to right. Make sense? right, so that's one possibility. This is the object moves. And the observer and I are fixed. All right, so the observer's head and the eye, let's see, are fixed. And then there's another case in which I will hold the object in one place, and then I have an eye here, and I move the eye over here. So when I start off on this side, and I have the retina coming around, draw it again over here. Should be the same eye, just moving across from left to right. And when I start off over here, I get the image on this side. And when I come over to this side, I get the image on the other side. Okay, way off there. Let's see. All right. So in this case, the eye moves and the object's fixed. So these two cases, I just want to say, if you imagine how the image looks along the retina, they should more or less correspond to the same thing. Now, one thing I've done here, I should admit, is this is a bit fictitious of a scenario because it's actually very hard to do this in practice. So if I want to try to look at an object, let's say, that's moving across my field of view, it's very hard to prevent your eyes from tracking it and doing smooth pursuit. It's very hard for you to disable your vestibulo-ocular reflex if you're moving around while you're fixated on something. So in fact, if I go back and forth like this, I'm looking at the camera right now, it's very hard for me to keep from continuing to look at the camera. It's like I have to put my fingers on the sides of my eyes like this, and then I can keep it from rotating. That's about the only thing I can do. Don't try that at home, I guess. Maybe that's hazardous to your health. So it's very hard to stop these reflexes. So given that that's the case, given that your eyes are going to be rotating anyway, that's going to make these two cases even look very similar to the case of no movement at all, right? Because your eye's rotating to keep a stable image on the retina. So I just want to point out all these cases, like even if your eyes are not rotating, these two are somewhat indistinguishable. However, when your eyes do rotate, in one case, if you're doing this, this will invoke the vestibulo-ocular reflex because you're moving your head back and forth. You could also do it with pure rotation, which is also translating your eyes through space. And then this corresponds to smooth pursuit if this object is moving slowly enough. So those are different modes of operation, which is part of the key of how the brain's going to distinguish between these. So let me give you how the brain distinguishes between these cases. Let me just list out the information that's being used. It's not just looking at a raw video signal, let's say, from the array of photoreceptors. It's got more sources of information coming together. So the brain uses more information to distinguish. We talked last time during saccade motions, there's saccadic masking or suppression, which when this happens, it suppresses the motion detectors. So while we're performing saccades, it's that the motion detectors that I just erased one of them, right? When I did the A, B, and C neural circuit, those outputs are suppressed. So already it's not going to be feeding motion detection information to your brain if your brain knows that you're performing saccades. So very interesting. So there's already some inhibiting that occurs there. Another thing that the brain uses is eye movement commands. So that's very interesting. Somewhere there's a command issued to let's say commands issued to contract or expand the muscles that move your eyes and rotate them, right. So if that's the case, it's a matter of sending those signals to the right place where perception is being performed, where the motion perception is being performed, and using that information. This is sometimes called by neuroscientists efference copies. Right, the motion commands or motor commands. It's very powerful information, right. The same thing happens in engineering. If I give a command to a robot that says move forward and then I observe what the robot's doing, you can make a lot better inference if you have access to the command. Oh, I know that the robot was commanded to go forward, right. If you program the robot yourself, you have that information. If you did not program the robot and you don't know what's inside of it, then you do not have that information, right. So this is extra information that's inside the brain throughout our neural system, let's say, and it can be used here. And then finally, one more piece of information is large scale motion. So if the entire scene is moving, what's usually the case? Is it usually the case that everything around us is moving simultaneously, or is it usually the case that in that event it usually means that we're moving, right? So if I all of a sudden notice a huge change, I go like this, right? It's very unlikely that all of you are rotating in some kind of roll, right. So that's prior information. If there's enormous large scale motion across the retina, probably you're the one that's moving, right. So that's falling back on it. You might remember I talked about the big swing illusion, where in an amusement park over 100 years ago, there was a bunch of participants sat down in a swing that was actually stationary, and then the entire room started rocking. That is such an unusual scenario. That would correspond to, you know, it corresponds to, in reality, everything is moving around you, but your brain interprets that as I must be moving and everything else is stationary, and that's what made people very sick and quickly believing that the chair that these chairs that they're in is spinning all the way around, that the swing goes all the way around 360 degrees, because it was tricking this information, basically, giving you an artificial scenario where the large scale motion assumption is in fact incorrect.
Professor,
yeah.
In both cases there is saccadic masking, even when we are moving on the object is moving.
Let's see. If we're saccadic masking occurring. So let's see. If we're holding stationary and we're looking at an object, well, let's define the scenario first. So is it let's suppose there's a stationary object, and we're looking around at the object, right? Like reading a book, for example. In that case, there's a lot of change across the retina, but the motion detection is suppressed, right? There's another scenario where, let's say, the object is moving slowly. In that case, there's no saccade. It's smooth pursuit. There is a scenario where the object's moving very fast, and some additional saccades are being inserted in order to keep up. But I think at that point, there's already been enough motion detected, I believe, from the smooth pursuit times in between the saccades. I'm no expert on neuroscience, but I'm trying to speculate as best as possible for those different scenarios.
Yeah, but still, how is it different from if the book is moving and you are moving the other way? The both cases are identical except the large scale motion.
No, I think the saccade motions we do, most often the saccade motions that we're doing, kind of the normal saccade mode, is to point the fovea or orient the fovea so that it's so that you're getting higher acuity images of a single fixed target. So those particular motions are interpreted because of this saccadic masking as that must be motion of the eye, just in that mode. All right, so in the case of smooth pursuit, it's usually not the case that you're doing extra saccades to try to take in all the information of the object by pointing the fovea while it's also moving. It usually, in the case of smooth pursuit, is trying to keep a stable image on the retina. So it's not a saccade case.
And is vestibular sense involved in this? That can also be an information.
That's a very good question. Yeah, I think that's reasonable. Why not add the vestibular sense here? I think that's reasonable. Very good. Yeah, absolutely. If the head is moving, there's going to be additional vestibular information. If the head is fixed, then it uses eye movement commands. So I like that very much. Yeah. So vestibular input if head moves. Or I guess your entire body could be moving without your head moving. If you're on some kind of moving cart, let's say, in a car, for example, then the head itself, it's still technically moving with respect to the world frame, but may not move with respect to your collarbone, for example. So, all right, very good. Any other questions or comments?
Two examples. One was using smooth pursuit and one was like vestibular ocular. But
yes.
The result is kind of like the same, right? Or is there some fundamental difference?
Smooth pursuit versus vestibulo-ocular. Well, vestibulo-ocular is using your vestibular signal, which I guess that's where it got used for one of the cases, right? So it's using exactly your self-motion in order to compensate. The smooth pursuit case is not your motion. It's the motion of the object you're trying to see, right? And so it's based purely on expectation of the motion of the object and trying to keep that stable across your retina, right? Both are trying to do some kind of, let's say, stable image on your retina, right? These are fundamental differences in whether or not the vestibular signal is getting used and evoked because of the motion, or you're just trying to track a moving target. And that's where the differences are. I'm just trying to say that kind of geometrically, in terms of just raw images, these look identical, but there's so much more information going, being obtained by the brain that it can distinguish these two cases.
Yeah, it seems like without that extra information, they're pretty much identical.
That's what I want you to think, yes. That's right. Like, wow, it doesn't have, you know, if just from images. So if we were to think like engineers and we just turn on a video signal and look at it and go, how does the brain know? Right? So I'm saying, yes, the brain knows. There's a lot more information here. So. All right, very good. And these are very good comments, very good ways to think about things. There's one more piece of information that's very naturally extracted from the images that change across your retina, and this is called optical flow. And this ends up being very important, and it's one of the most important aspects in relation to motion sickness, or simulator sickness, I should say, not necessarily motion sickness, because the VR participant is not necessarily the one moving. All right. Usually we say motion sickness for something you might get from moving in a vehicle, let's say moving in a car while being a passenger especially. That's motion sickness. Simulator sickness would refer to what you get from a virtual reality experience, for example, where you may perceive your own motion but you're actually not moving. So those two are kind of inverses, motion sickness versus simulator sickness. So optical flow. So what happens is, in this case, the brain can keep track of images on the retina, or features, let's say, on the retina. So there may be some particular feature. I see a red dot above the camera there, so I can move around in some way, and that dot is going to appear somewhere on the retina, and I can keep track of that, right? And if there are several dots, then if I get closer to them, the dots will start spreading apart. If I go further away, they'll start contracting. If I go to the left, they'll move to the right. So this is called optical flow information, where features are moving in the image. So our brain perceives them to be the exact same object or element in the world. There are a bunch of them, and we perceive a kind of general flow because of that. So it's tracking movement of features on the retina. And we end up with a kind of vector field, kind of velocity field on the image plane. Or roughly the image sphere if you think about the way the retina is shaped. It's fine. So if we think about various self motions, as I just illustrated, if I'm going forward, then the flows tend to be outward from the center. Correct? Also, the flows tend to be faster at the periphery than straight in front of me. So not only are there directions in the optical flow, but there's also a magnitude. Right? So these are full-fledged velocities in the image plane or image sphere, if you like to view it that way. If we go backward, then these reverse. And if we go to the left, then we see flow to the right. So when I move myself to the left, I see you flowing to the right. Also, if I turn myself counterclockwise, I also see flowing to the right. So I see also counterclockwise. Of course, I'll get flow in the opposite direction by going right or clockwise rotation. Our ability to perceive optical flow turns out to be strongest as I look forward right about here. I think somewhere around 20 to 30 degrees off. This is the place where you have a very high density of rods, if you remember when we looked at photoreceptor density. And generally it's very strong in the periphery. Right, so that means that if there's some kind of motion in the periphery, we respond very quickly to that, turn our heads. Could be a predator, right? Maybe some evolutionary reasons for that. So just generally speaking, it's stronger in the periphery. I believe it peaks around 30 degrees or so. And then it starts trailing off again because of the low density of photoreceptors that we have as we gradually go to the side, gradually look to the side. So based on this optical flow, we have a big problem in virtual reality. A big problem. You've experienced it in the lab already, I'm sure. Which is the illusion of self-motion from optical flow. This is called vection. I've said this before. If you're sitting stationary in a train and the train next to you starts moving, you're looking out the window, maybe you're not even paying a lot of attention, in fact. It's your peripheral vision that notices that there's some motion to the side. You get a feeling like you're going backwards all of a sudden, right? So it's the illusion of self-motion. When you grab onto a controller or you hit the right keys on the keyboard and you move your avatar around in virtual reality, you perceive an optical flow that gives you the illusion of self-motion. Every time you do that, that is a mismatch between your vestibular signals, which can measure the true acceleration, and your eyes, which are trying to also measure the acceleration. And your eyes are being fooled, but your vestibular organ is not. That mismatch causes a significant amount of nausea in people. And in fact, it's very easy to make horribly nauseating experiences. I believe one of the worst things you can do is to make it appear that you're virtually rotating and then put some kind of sinusoidal oscillation into it at about a couple of hertz. And people will get sick very fast like that. You want to have a fun project to do in the lab. Try to make the most sickening experience you can. It should be some kind of rotational thing. Experiment with different rates and you know, compete with your friends for the prize of the most sickening experience. So that's the problem, is that the vision system and vestibular system are in conflict. Again, I talked about decision theory. Your brain is trying to fuse information from multiple sources. Normally in the real world there's a consistent picture. Now there's a big inconsistency. So being nauseated is not necessarily a surprising response to that, right? Because maybe another thing consistent with that is you've been poisoned, right? So it's good to eject, right? Who knows? So it's hard to know exactly what all the mechanisms are and why this is happening, but it may be that you get sickness because the body believes that something bad has been ingested, right? And so why else would there be such a strange conflict? It would not be able to take into account modern engineering as one of the plausible hypotheses unless you experience enough of this, and then eventually you may be able to train yourself to overcome this mismatch. That may be a lot of work to overcome. Some people may learn it easily, some may not. Could depend heavily on age, gender, many other kinds of factors. I should give one simple example of this. We did some experiments. I think it's worth considering just to try to alleviate these kinds of problems. This has more to do with user interface design or avatar control or movement, things like that. But I just want to give you a very simple example of this problem and how it tends to behave. So, so a very simple example is suppose you want to ramp up your avatar or character motion. In other words, suppose you believe you're in a virtual world, right, in this beautiful world. You'd like to move forward. You grab onto a controller and you want to just start walking forward. I want to ask you which of the following two are best to do. So you'd like to get up to some fixed walking speed, and so this is your speed here. This is time. And so one scenario is you'd like to get up to this speed, let's say. So one scenario is you just gradually ramp up and then get to your speed that you'd like to be at. And then the other choice is you just decide that you're going to, rather than make a continuous change, you just discontinuously jump to the speed you'd like to be at and go forward. So this one corresponds not at all to the real world, because normally you cannot accelerate at an infinite rate, right? But this is what you could do. So you just pulse and all of a sudden, bam, you're walking at full speed. Which one of these is a more comfortable experience for virtual reality? Let's call this scenario A, scenario B. Who thinks scenario A would be more comfortable, right? So this corresponds very closely to the real world. You gradually ramp up your speed. Is this more comfortable? Scenario B, is this more comfortable? Okay, I've seen, I think, 0 hands being raised, but some little head nods here and there. So here's what happens. What's that, B? I'm hearing more B's now, right? Right. I should, you know, professors are always trying to trick you, right? So it cannot be the, you know, this looks like the obvious kind of comfortable sort of answer. Just make it maybe like it would be in the real world. I start off and I just gradually get up to a speed and then I'm comfortably going along. Well, what happens here in the first case is there's an interval of time between these lines here. During this interval of time, there's a mismatch. Right? There's a vestibular mismatch. So your brain has the opportunity to latch onto a mismatch over some period of time. And it builds a lot of confidence, right? You imagine the brain is going, oh yes, I'm certain there's a mismatch. It's been going on for a second or two, right? Whereas in this case, there's a mismatch only at some tiny fraction of a second, right? So just if you want to look at the limiting mathematical case, then maybe it's only a single 0 length interval impulse, right? Bam, there's some mismatch. This, the brain may rule as an outlier. It may say, okay, there's always outliers in the data, a kind of hiccup, it's gone. So this seems to be perceived as an outlier. Like what was that? Some big flash, some huge mismatch, probably junk, discarded. This one, the brain's very certain. And the brain is right, you know. There is some very consistent mismatch happening here. So, so this ends up being very uncomfortable, A. B ends up being the one that's more comfortable. This is one of the reasons why you'll see this as well in some of the apps where if you're rotating your character, you may notice that some of them, when you press the button, it rotates a fixed number of degrees each time rather than smoothly rotating. Smoothly rotating is very nauseating, but jumping discretely is not as bad. But if you jump discretely 90 degrees each time, then you're not even sure which way you're facing anymore. So you have difficulty of being disoriented. You're not really sure where you're facing anymore. It'd be great to just point and click where you'd like to go and just be there. If we could do that in the real world, it wouldn't be so bad either, right? So that's fine. But you also start to get confused about your where you are in space. So that's a trade-off you have to deal with. So we want to minimize this kind of discomfort due to this vestibular mismatch with your visual cues. But at the same time, we also want to make sure that that your spatial reasoning and awareness remains intact. That's a challenge we face. If you can make progress on that for your class project, I would be delighted. You know, so it's a great challenge. All right, questions about that?
Is there an upper limit to the constant velocity at which friction does not appear?
You mean maybe a lower limit, like if the mismatch is sort of small enough? There's another limit, which could be that maybe I make this slope so low that and it's so gradual that it may be comfortable, right? So that limit could exist.
I'm asking about the limit to the speed speed itself.
Yeah.
The upper limit to the speed.
So if I raise this up higher?
Yeah. Will it cause?
I think it will tend to be worse. But, there are interesting questions about going up to speeds that are familiar to us, right? Like we may be, if we believe we're in a car, we may be accustomed to going up to some speed and then remaining at that. And if we see stimulus that's like a bunch of roads around, that may be comfortable. If we are in a building and we go up to some speed that's quite outrageous, faster than we could run in the building, that may be uncomfortable. But maybe it doesn't correspond to anything that we've ever seen before, so maybe it's in fact not uncomfortable. I don't know, you know, there's a lot of things going on here. There are a lot of prior cues. Our brain is basing its conclusions, this kind of unhappiness that comes up because of the mismatch, on a lot of prior information. So that's why, you know, I wonder about when I showed you the Birdley demonstration of the flying. You go flying over virtual San Francisco, for example. That does not correspond to an experience that we've ever had before in the real world. There's also a motion platform that's helping your vestibular cues, but there's a lot of vection going on here, I think, nevertheless. But that's not the same as this scenario like here, where you're just doing ordinary everyday walking, which your brain is quite familiar with, and there's a very obvious mismatch. So it may be helping it to be worse by doing things at exactly the same kinds of speeds that we're normally comfortable with. So it's providing everything in perfect alignment except this one mismatch, and the brain may have an easy time. If a lot of things are mixed up, maybe it won't, you know, maybe it will not be as sickening. I really don't know. I'd have to do the experiments on a case-by-case basis.
So there's another problem, like in virtual reality at least, like most of the points are discrete, and you cannot have a smooth speed increase. So it will be like you're jumping from one point to other at various speeds. So that might cause like a point might be available at one point, and suddenly it is at another point. So
yeah, very good. I think that's a very good point. In fact, that's going to lead into my next topic, which is apparent motion. So if you have something that's really, if you have a sequence of images that are being generated by a digital system, and you know, under what conditions do you perceive that as a continuous motion? Under what conditions does that feel like the real world? Do you perceive that like the real world? And so there's a nice sort of gradual entryway based on your question into the next topic. You know, fundamentally, I don't really make too much of a distinction between continuous versus discrete. If the discretization intervals are so small that it very closely approximates continuous, way below any sensible levels that could be detected by the body, then the two are essentially the same. The universe itself, is it discrete or continuous? Well, I think it's more discrete actually than continuous when you look at it carefully, when you move beyond Newtonian mechanics and into quantum mechanics and things. So the discrete versus continuous itself isn't a extremely important distinction in this context, but when it is discrete, what exactly are the rates, and are those perceptible? And that ends up being very interesting.